Hi everyone. Today let's talk about chapter 2, proofs. Proofs are super important in math class, especially for your upper level math class. It's really a good foundation. So I really hope that all of you can pay more attention in this chapter because many students find doing the proof is challenging because there are so many details, so many steps we need to support one another. Okay? So section 2.1, mathematical systems, direct proofs, and counterexamples. A mathematical system consists of axioms, definitions, and undefined terms. Axioms are assumed to be true. So we assume the axioms to be true, so we don't need to prove it. We assume them. So such as we know 1 plus 1 is 2. We don't prove it. We just assume that's the case, right? Definitions are used to create new concepts in terms of the existing one. Some terms are not explicitly defined, but rather are implicitly defined by the axioms. Within a mathematical system, we can derive theorems. A theorem is a proposition that has been proved to be true. Special kinds of theorems are referred to lemmas and corollaries. A lemma is a theorem that is usually not too interesting in its own right, but it is useful to proving another theorem. A corollary is a theorem that follows easily from another theorem. So usually, we have a big important theorems. So how do you prove this big important theorems? We might separate into a couple steps. And those little steps, we can call them lemma. So lemma are some small theorems. Then by itself is not quite interesting, but all the couple of lemmas together can help us to prove a big theorem. And the corollary is usually some easy theorems follows from a big theorems. So in general, I would say lemmas comes before a big theorems and the corollary comes after a big theorems. Okay? An argument that establish the truth of a theorem is called a proof. Logic is the tool for the analysis of proofs. So here, let's look at some example. Euclidean geometry is an example of a mathematical system. So we have tons of axioms and definitions and theorems. So here I just picked some of them just to illustrate. Okay? So some axioms. Given two distinct points, there is exactly one line that contains them. Well, so we have two distinct points. Well, we know that 2 points fix a line, right? How about parabola? Okay, 3 points can fix a parabola. Okay, so these are axioms. We just assume them to be true. Next, given a line and a point not on the line, there is exactly one line parallel to the line through the point. So we have a line and we have a point. Well, then there is only exactly one line that passes through this point and parallel to our line. Okay, so these are axioms. We just assume them to be true naturally. Okay, and we have some definitions. Two triangles are congruent if their vertices can be paired so that the corresponding sides and the corresponding angles are equal. So, okay. So we have two triangles. They are congruent if the corresponding sides and the corresponding angles for each of the pair are equal. Okay? So that's the definition of congruent. Next, two angles are supplementary if the sum of their measure is 180 degrees. So the picture is like this. So we know this is alpha. This is beta, then we know they're supplementary angles. Okay, because the sum of them is 180 degrees, which is pi. Okay, So here are some examples of definitions. Next, let's look at some theorems. If two sides of a triangle are equal, then the angle opposite them are equal as well. So we draw the picture here. If the two sides are equal, then the angle opposite them are also equal as well. Okay, this is a theorem. And we can prove it. Okay, we're not going to prove it here, but we know a theorem can be proved to be true. Next, if the diagonal of a quadrilateral bisect each other, then the quadrilaterals is a parallelogram. So, okay, we know that if the diagonals bisect each other, then this quadrilateral is the parallelogram. Okay? Next, direct proof. Okay, so theorems are often of the form that, like for all x1, x2, xn in some sets, and usually these belongs to the domain of closure. Okay, usually when we domain of disclosures. So usually when we work with real numbers, then it's real numbers. Sometimes it could be positive integers. It really depends on the problem. Okay, so we have the domain of disclosure. And then we have some hypothesis or assumption. Okay, so these are the hypotheses. Or we can say assumption or premises. Then this is our conclusion. Okay, so last time we talked about argument, and we have hypothesis, a series of hypotheses and premises. At the end, we get a conclusion. Okay, so here's an example. We have definition. An integer n is even if there exists an integer k such that n equals 2 times k. An integer n is odd if there exists an integer k such that n equals 2k plus 1. So this is definition, and we want to prove that for all integers m and n, if m is odd and n is even, then m plus n is odd. Okay. How do we know that? Okay, let's try to understand this by plotting in some numbers. So if m is odd, well, can you give me an odd integer? Let's say 3, right? Can you give me a even integer? Well, a 2, easiest one, right? Then, okay, so we have 3 is odd, and the 2 is even. Then 3 plus 2 is 5. You can see 5 is odd. So some examples can help us to understand like what this lemma, what this sentence is talking about. Okay, but in order to prove it, we need to prove it for all integers. We cannot just pick some numbers and show it works. Okay, so to prove it for all integers, we can say let m and n be arbitrary integers. Okay. And also we need to assume that m is odd and n is even. So let's separate them. Okay, so we let m be an odd. Okay, let n be an odd integer. And oops. Okay, so let me fix this. Okay, so let n be an odd integer, and we also can let let's see. Okay. Oops. Something wrong with my word. Let me fix it. Okay. Okay, so let n be an odd integer and n be an even integer. Okay, so that's the first sentence. We want to like define our m and n, and then look at so the information, because m is odd. What does it mean by saying is odd? Okay, so we say since m is odd, by the definition of odd, we know m equals 2 times k for some integer k. Okay, and next, because n is evens, then, oops, sorry, I think I just flip it. Okay, because m is odd, so m is 2k plus 1 for some integer k, and because n is even, then n equals 2 times, let's say, l, okay, for some integer l. Okay. And then next, we want to look at what is m plus n. Then m plus n equals, well, we have 2k plus 1. That is m, and l, n is 2l. Okay, so we want to show it's odd. So which means we want to express this guy in terms of 2 times the integer plus 1. And how do we do this? Well, we can move the 2l in front. So then we can have these. The next step, you see, we can factor out the 2. Then we have k plus l here. Okay? And now we have the good format. We have 2 times, because k plus l is an integer. K is integer, l is an integer, then k plus l is an integer. So we have 2 times the integer plus 1. So m plus n is odd. That's finished our proof. So here, I want to emphasize when we do the proof, is really like building the bridges. So it's like we have 2 islands here. So the first island is like our hypothesis. Okay, our hypothesis, and the final destination is our conclusion. How to connect them? Well, then we're gonna build the bridges between them. Okay, sometimes people can start with the hypothesis and then they build the bridges until they reach the conclusion. Sometimes people can start from the hypothesis, go and build one bridges, and then look at the conclusion and find another bridges, and then they connect them. Okay, so it's like building the bridges. Like our examples, we start with odd integer and even integer. So that's why this is our first step. We define the odd integer m and the even integer n. And then we use definition of odd and even integers. A small things we need to be careful is, well, this k and this l, they should be used different letter. Okay? You cannot use the same k. So if you use the same k, what does that mean? Well, you're talking about m is 2k plus 1 and n is 2k. So m is n plus 1. So you create m equals n plus 1, which is not correct, because in our problem we just assume m to be any odd integers and n to be any even integers. We don't require they are different by 1. So we have to be careful. Okay, everybody? And at the end, we know that we want to show that m plus n is odd. So we know that we want to have the format 2 times some integer plus 1. Then we can like connect those bridges. So far, so good, everybody. So today we will do lots of examples. Okay, let's look at the next one. Okay, so prove that for all rational numbers x and y, x times y is rational. Okay, so start. So let x, y be rational numbers or arbitrary rational numbers. Okay. Then because they are rational numbers, okay, so we say since or because since x is rational numbers. Okay, what does rational numbers means? Then we have x equals p over q. We can say p1 over q1 because I still have my y. Okay, so p1 over q1 for some p1 and q1. Oops. In z. Okay, so this is another way to say they're integers. We can say for some integers p1 and q1. We can also say for some p1, q1 in z. Z is the set of integers. And also we can say since y is a rational number, then y equals p2 over q2 for some p2, q2, which is our integers. Okay, and then, we can continue. We want to look at x times y. What is x times y? Well, we have p1 over q1 times p2 over q2. Well, we can combine them, right? Then we have p1, p2 over q1 and q2. Notice that the top and the bottom in the numerator and denominators, they are both integers. Okay, so that's why by definition, so we can say xy is rational. So far, so good, everybody. So, yeah, during the proof, there are a lot of like words you might consider to use. You can use because, since, so, therefore, hence, etc. Okay, or like order, like first, second, at last, finally, something like that. All right, let's continue. Example proof for all sets x, y, and z. X intercept y minus z equals x intercept y minus x intercept z. Okay. So here, what we did before is we can use a Venn diagram to show the region. But today, I really want to show you how to prove it. Okay, but we can draw a Venn diagram like to see what happens here. So we have x, y, and z, right? And we have two Venn diagram, x, y, and z. So x, y, z, x, y, z. Okay, first, x intercepts y minus z. What is y minus z? Y minus z means it's in y but not in z. So here, well, x intercepts y minus z. So x intercept this region is, so we have these small pieces. Okay, next. We have x intercept y here, x intercept z is there, and we want to have x intercept y minus x intercept z. Then what do we have? We have this guy, right? So you can see in both pictures, we have the same region. So we know they're equal. Okay? But today, I really want to show you how to prove it like using definitions. Okay? So equal means this guy is a subset of this guy, and the right hand side is a subset of the left hand side, and then they are equal. Okay, so here we have two directions. Let's start with this direction. Okay, this direction, which means we want to show, okay, so we want to show x-intercept y minus z is a subset of x-intercept y minus x-intercept z. Okay, so how do you show it? Well, you start with an x within this set, and you want to show that the x also belongs here. Okay, so let's start. Okay, suppose x in x-intercept y minus z. Okay, and then we want to show the x is also belongs to the right hand side. Okay, so x is in x-intercept y minus z, so that means x is in x and x is in y minus z. Okay, and because x is in y minus z, what does that mean? Okay, so we can get x is in y and x does not belong to z. This is by definition of set minus. Okay, and then next, wow, let's see. Because this is our goal, you can see x is in x and x is in y, so we can say since x in x and x in y, then we have x in x-intercept y. Okay, everybody? And also, well, if we use a lot of since, then we can use because. So because x does not belong to z, and we know that x minus z is a subset of z, right? X minus z is a subset of z, but because x is not in z, so x does not belong to x minus z as well. Okay, so now we're done because we have x. Okay, so we can use since again, since x in x-intercept y and x is not in x-intercept z, so we have x is in x-intercept y subtract x-intercept z. This is by the definition of set minus. Okay, so that finished one direction. You can see each step we are using a definition or a rule. Okay, next direction, we want to prove the right hand side is a subset of the left hand side. So we want to show that x-intercept y minus x-intercept z is a subset of x-intercept y and z. Okay, y minus z, sorry. Okay, so similarly, suppose x in x-intercept y minus x-intercept z. Okay, then what does that mean? By the definition of set minus, x is in x-intercept y and x is not in x-intercept z. Okay, so x is in x and y. What does that mean? Well, so because x is in x-intercept y, by definition of intersection, we know x is in x and x is in y. Okay, everybody? So let's see here. So look at our goal. This is our goal. Remember, it's like we're building the bridges to connect different islands. So this guy, we already proved that x is in x. Okay, and then here we already proved x is in y, but so we still need to prove x is not in z. Okay, and here because x is in x and x is not in x minus z. Sorry. Let's see here. Because x is in x and x is not in x intercept z, then x is not in z. Why is that? Because otherwise, if x is in z, but because x is already in x, then we will get x is in x intercept z. But this is not the case. Therefore, x cannot be in z. Okay, now we have almost done. Since x in y, but x is not in z, so x is in y minus z. This is by definition of set minus. Finally, because x is in x and x is in x minus z, so if you don't want to use so, you can use hence, therefore, etc. So hence, we have x in x intercept y minus z. And then combine both direction. Let me see. I need one more line here. Okay, so combine them together. We can say therefore, or thus we have x intercept y minus z is equal to x intercept y minus x intercept z. And that finished the proof. Okay, so far so good, everybody? Yeah, so here I also put the useful words let, suppose, assume, first, and last, finally, because, since, so, hence, therefore. Okay? So you can use these words in your proof. Okay, next topic. Disproving a universally quantifier statement. So we call in section 1.5, in order to disprove for all x p of x, we simply need to find one member in the domain of disclosure which make p of x false. Such a value for x is called a counterexample. Okay, so yeah, for universally quantified statements, if you want to show it's true, then you have to do a proof like what we did, okay? You need to show it is true for all values in the domain of disclosure. However, if you want to show that statement is false, then you just need to find a counterexample. Okay, so let's look at our example. The statement for all n in the positive integers, okay, 2n plus 1 is prime, is false. Okay, let's see. Let n be a positive integer. Is that 2n plus 1 is always prime? Let's find a counterexample. Positive integers, what are positive integers? Is 1, 2, 3, 4, etc. Right? Let's see. If n is 1, then let's see. Because when we want to find a counterexample, we can go down the list and then until we find 1. Okay? So let's see here. 2 times 1 plus 1 give us 3. 3 is prime, so nope. 2 times 2 plus 1 give us 5. 5 is prime, nope. 2 times 3 plus 1 is 7. 7 is prime, no. 4. 2 times 4 plus 1, oh, 9. 9 is not prime. See, we find the counterexample. So here we can say the counterexample is we can pick n equals 4, then 2n plus 1 is 9, is not prime. Okay, of course you can find other numbers. I'm sure a lot of number works. For example, 7 works, right? 7, then 2n plus 1 is 15, and it's not prime. There are lots of counterexamples in this case, okay? So you don't need to pick the one I pick. You can pick many, as long as 2n plus 1 is not prime, okay? Let's continue. So if the statement A intercept B union C equals A intercept B union C for all sets A, B, C is true, prove it. Otherwise, give a counterexample. Okay, let's draw them. Okay, let's draw them. To figure out whether it's true or false, first I would like to draw them. I will draw the Venn diagram to see whether they are the same. If they're the same, we can write a proof just like what we did in the last page. If it's false, then we can create some counterexamples, right? So 3 sets, we have A, B, C. A, B, and C. Okay, left hand side, A intercept B, A intercept B, this is A intercept B, union C, so the C is right here. So union means is this region, right? This whole region. Okay, this is the left hand side. How about the right hand side? The right hand side, we first have B union C. So B union C is right here. And then A intersect them. Well, when you do intersection, what happened? Okay, let me see. Well, intersection, then we have this guy. Right? Are they the same? No, they're not the same. So let's give a counterexample, okay? How do we give a counterexample? Let's just put some elements in those regions. We can put the elements here 1 and 2, 3, 4, 5, 6. Something like that. Okay. So here, the counterexample. Okay, A is 1, 2, 6, right? That's the A. And B, what's B? B is this circle. This circle is 2, 3, 4. And C is what? The 4, 5, 6. Okay, now on the left hand side, A intercept B union C is the set. What are the numbers in the green region? Okay, that's 2, 4, 5, 6. And then on the right hand side, A intercept B union C. So those are the numbers in the blue region, which is 2 and 6. Okay, you realize that the middle guy here, I didn't put a number there because it does not matter. You can also put a number there. It will give another counterexample. There are tons of counterexamples, and we just need to pick one. Okay, so there are a lot of answers to this problem. So far, so good, everybody. Okay, so this is about counterexamples. And that's it for today's class. Okay, have a nice day. Bye.